Let's look at a simple example of polynomial long division. The motivation right now for me is the context might be that you're integrating a rational function, and if the degree of the numerator of that function is greater than or equal to the degree of the denominator, you're going to want to do a long division to simplify that to be a proper rational function before you might do partial fractions or some other technique, a substitution, something like that. So it really is a must if you're in that improper situation. The techniques that you would use in the proper situation just won't work, and you need to do this division. So Algebra 2 review, it's something that people tend to not like too much in Algebra 2, and then we don't practice it very much, but let's run with it. For me, I didn't understand the ordinary long division algorithm, I don't think that deeply, with decimals until I learned this in algebra. So that's actually not a bad reason to learn it. So we're going to set up our usual tableau. Here's the divisor. Here's the dividend. I've got some sort of semblance of what you usually write as your little the box that you put the dividend into. And just like with ordinary long division, you don't focus on the whole divisor and the whole dividend. You just look at the biggest part. In this case, instead of the top digit, which is what you'd focus on in a decimal long division, you look at the highest power. It's really quite analogous. And you excuse me, and you just say, how many times does x squared, sorry, I keep right clicking, how many times does x squared go in excuse me, into x cubed? Well, that goes in x times. And then you just say, well, okay, I'm going to see what x times this is and see what's left over, and then I'll deal with the leftovers. So you multiply that partial quotient times your dividend, and you're going to get x cubed plus 3x squared minus 7x. Okay, let me try and align that a bit. I'm going to align this a bit too, just by putting in some extra spaces. It doesn't really want to align it. Okay. And I'll put a little underlined bar there, as you usually would. Okay, and then we're going to subtract. So x times this dividend gets us somewhat close. In particular, it does nail the x cubed by design. And so the remainder is going to be simpler, and then we'll work on the remainder. So when you subtract, the x cubes cancel. You get minus 2x squared. And then minus 11 minus a minus 7 is minus 4. X, and then don't forget to bring the plus 9 down. I forgot to do that when I was testing this out, honestly. And let's see, to line it up, I'm going to put little spaces right there. Okay, so now I need to see how many times, if at all, does x squared plus 3x minus 7 go into here, but really I just focus on matching the x squareds. How many times does x squared go into minus 2x squared? Oh, minus 2 times. Okay, I can kill some of those spaces. Okay, so if you had minus 2 times this numerator, times the divisor rather, you're going to get minus 2x squared. And then minus 6x. And then plus 14. And let's put some spaces in there. Let's line it up. Boop. Okay. And we're going to subtract, so I'll put a little underline there. Okay. So far, what have we done? We've really said x minus 2 times x squared plus 3x minus 7 will get you, the x cubed will match, and now we're going to see that the x squared terms will match, and it will get you something that's very close to x cubed plus x squared minus 11x plus 9, but with a certain leftover, and at this point, we'll actually be at our remainder. So, I really am not right-clicking, and it thinks I am. Okay, so the x squared cancel by design. Minus 4x minus 6x is a plus 2x. Plus 9 minus a 14. Remember, we're subtracting everything on the bottom. Minus 5. I'll line that up. And there's our remainder. How you know it's the remainder is you've got a polynomial that's lower degree than the divisor. There's no way you can multiply x squared by some polynomial and get a 2x minus 5. So I'm claiming, let me just delete this last unnecessary row, I'm claiming that if we want to write it out in just sort of normal algebraic notation, x minus 2 times x squared plus 3x minus 7, that's not quite going to be x cubed plus x squared minus 11x plus 9, but that plus 2x minus 5 should be this guy. That is what this is supposed to demonstrate. And that's because if I take x times this, I get this first thing that I subtracted off. And then if I take minus 2 times the divisor, the denominator, I get this thing, which I also subtracted off. When I subtract both of those off, that's all I'm really doing, is I'm taking this original numerator and subtracting x times the denominator and subtracting off minus 2 times the denominator. When I subtract all that off, I should get 2x minus 5. And we can check it. I won't show you by hand, but if I do like an expand command on the calculator, you get that, okay? And then if you add the 2x, sorry, the whole thing is matching. I forgot to put the 2x minus 5 in. So it really does match. So this is something you're going to have to do. So if we write it out in terms of fractions, for example, maybe in the integral context, there's actually a lot of places, the further you go, where you might want to do partial fractions. A good example is what's called Laplace transforms. They're related to integrals, but they're not the same thing. That's going to be the integral of, so let's see, in terms of a quotient statement, the quotient was x minus 2. That's really nice and simple. And I'm just going to separate that as a completely different integral, plus the integral of just 2x minus 5. Hey, I put that in the wrong place. Over this denominator. That is something that you would then do, you'd look and see if this denominator factors. If it doesn't, you're going to do a complete the square, do some maybe some trigonometric substitution, things like that. If it did factor, then you would do partial fractions, all sorts of techniques. But that's all I wanted to show you in this video.